All right, so I wanted to create a quick video looking at doing some non-parametric modeling and talking about that in a little bit of detail in case we don't have time to cover it in class today. I'm going to make a simple 1-inch cube and set that cube to be a ABS plastic. And then I'm going to run some simulations with this just to show you guys some of the, I guess, the technicalities of running this non-parametric kind of test. So there's my 1-inch cube. I'm going to make it regular ABS, not polycarbonate ABS. I'm just going to go to the plastics option and apply that. And then I'm actually going to start off running a regular simulation, just a static simulation with a load on the top and a force on the bottom. So putting this in pure compression. That's probably the simplest test you could ever run in SolidWorks, and honestly, probably not even worth running because you could just divide force by area and get stress and not have to run this in SolidWorks at all. But again, it's not a bad example. So we'll do 100-pound force on the top, which again, for a 1-inch block is quite a small amount of force. And so I'm going to run this. The reason I'm running this in the simulation first is that generally it's a good idea to get an idea of what your factor of safety and your maximum stresses inside the part are before you move to a parametric test. In this case, my maximum stress in this part is 1.2 megapascals, which is a factor of safety of probably around 40 if I'm making this out of ABS. So ABS, you expect to see maybe 38, 39 as a lower end of yield stress, at least in compression, without worrying about things like interlayer adhesion or 3D printing or anything like that. And you might see a significantly higher strength value than that, depending on your manufacturer and the processing techniques that are used. So a lot of variations in plastic, but again, a very high factor of safety. With a setup like this, if I want to run my topology study to do a non-parametric design, I'm going to do the same setup in the topology study options. So again, I'm going to use a fixed geometry on the bottom, and then a 100-pound load on the top. And if your model has, a reasonably low factor of safety to start with, then it's actually a little bit easier in some respects because it will not have to remove as much material to achieve a kind of a more appropriate factor of safety of say like 2 or 3. But if you are doing this, chances are you do have a pretty significant amount of material to remove, and so these kind of considerations that we'll talk about here become important. I'm going to start off by creating a mesh that's very coarse. And that's going to make this much easier to solve. I don't know why I didn't actually create the mesh. From a simulation standpoint, it'll be a lot less nodes, but it's also going to make it less accurate. And I'm hoping to be able to show you guys what happens. That's still pretty. Let me try this one more time. I want this to be fairly coarse. That's a little bit more coarse. That's probably okay to start with. And so, this is going to have to try and remove a lot of material, but these elements are pretty big. So when it removes the material, it's really removing these elements from the mesh and then resolving. And so that can be difficult for this to solve because I guess I'll find the goal. So I'm going to set the goal as minimize mass subject to a factor of safety constraint. The factor of safety, try and get that down to a maximum yield stress or a yield stress of 20 megapascals. So just sitting there, I'll pull that out so you can see it a little bit better. So 20 megapascals. I guess one of the things to watch out for is if you change the units here, it does update this. So if you type in the unit first and then change it, make sure you type in the value again if you're typing in the value you want. Oh, sorry, I don't want factor of safety. I want stress constraint. Factor of safety. No, I want stress constraint. Oh, you know what? I think I used the scroll wheel on here on accident. Try that. Okay. So I'm going to run this. It's going to take a little while to run. So hopefully I may pause the video and then unpause it when it's done. But we'll see kind of what the timeline looks like. All right, I'm going to go ahead and pause this video, and then we're going to time skip to when this is finished running. All right, so this is finished running. And we got a result here. It's quite a bit thicker than I expected. Let's look at the results inside the editor here, so we can use the slider to look at kind of what variance we're getting out of this. Okay, and so this is what I'm talking about here. If I take this out, you'll notice that the behavior here isn't really what we expect it to be. Because the stress inside this part is so consistent, it has a really hard time of making a model that actually shows where the material needs to be. In fact, it's obvious that this part wouldn't work with any of these lighter options. Going through this system, right? So, this far side of the slider should really, isolate down to what is a reasonably good part based off the stress results. But again, since we don't have variation in stress, this doesn't give us a really very realistic result. And even if I come to a moderate level here, right, or pick something that's fairly heavy, and then I try and smooth the mesh, we still don't get kind of a viable output. So, I just wanted to look at this as one of the potential limitations of doing this kind of systems, that this doesn't work well for very simple stress distributions. It works much better for complicated stress distributions where you have higher and lower areas of strength. I want to do this one more time with a higher density mesh and see if it gives me a little bit more of an accurate result. I'd like to see something where we have more like pillars built out into this model. So let's change our mesh settings. And saying that if I remesh it, I'm going to lose my topology settings. Then I'm fine with that. So here I'm using the opposite extreme. I've turned the mesh quality all the way up. And generally in a topology study, what this is going to do is it's going to make it easier for it to converge on a solution, but harder for it to run each individual iteration. So the individual iterations will take longer, but the total number of iterations will be less. Let's try running this. Again, I expect this one to I don't know if it's going to remesh if I do this or not. I'm going to hit no, just because I want to use the mesh that I have already generated. I'm hoping it used the mesh I generated last time. I don't know why it didn't give me that pop-up. All right, let's go ahead and pause the recording and I'll resume it once it's done running. So I'm getting impatient with this thing. It's taking this about 2 minutes for it to run each iteration, whereas the previous simulation ran about 20 iterations in about a minute before it converged and finished. I'm not sure exactly how long, because these figures go away as soon as they finish, but quite a bit faster. You can see here we're on the 4th iteration. Our stress values are still not up at the target value, so it hasn't gotten up to that that kind of conversion point yet, but I'm going to go ahead and stop this, and it should finish the current iteration and show us the current result at this value, which is about half of what we're trying to get to. So I'm going to say yes to save the analysis. It looks like it did finish that last one, which gets us pretty close to where we wanted to be, which is, fine. And then let's go ahead and go ahead and close those. I'm not sure if there's a way of seeing the convergence plot after you close it. That'd be interesting to look at. It looks like it's still thinking. Maybe give it another second. All right, so it finished here. Still have an error because this was not actually finished running. But let's take a look and see what the results slider looks like on this and see if we get something that's a little bit more realistic. So still not getting a good behavior because, again, of that very even stress distribution inside the part. You can see that kind of the top and bottom wall or floor and ceiling is a little bit more realistic. I'm gonna try smoothing the result around the middle here and see if we can get a little bit more of a pillar structure built up into this model. There are probably voids in here that we're not seeing at that point. Because again, it's trying to remove basically the entire middle section of the model at the same time. Because all of those having the same stress value. There we go. So that's a little closer to what we might want to see, and then kind of an accurate simulation where you have this porous material built off of, try not smoothing. Option to unsmooth this. I just got to uncheck that and then it comes out. I don't know if I can do ISO clipping on this result or not. It looks like I can. Let's do section clipping. So you can't see the inside of there. There you go. And so you can see we have a little bit of like a hollow shell in this case, as opposed to a pillar design, which would be a better kind of use of material than the other result. But still, again, not great results inside this for this simple simulation. All right, well, that's all I want to show for this section. Hopefully that gives you a kind of a good idea of what not to do in simulation, and we'll try and give a better example of kind of a good use of the topology study in class today.